So this work we've been doing as part of the AMD open source debuggers project, and I've got a few links here, they're at the end as well. And our goal really has been to get heterogeneous computing debugging to kind of be viable. And the thing we had to kind of wrestle with is the fact that GPUs do have a bunch of kind of novel things. They have multiple address spaces, which are kind of hardware supported things with different instructions to access them. They have a lot more scalar registers than traditional CPUs have. And then they have these interesting wide and many vector registers. And the big thing about the vector registers is the hardware will execute instructions in a SIMD-like manner. And we get the compiler to actually map our source languages where a thread of execution of the source language is kind of using a single lane of the vector register. The vector register has many slots, and this means that if we have a variable that takes up more than one of those slots, we have to actually kind of spread it across that slot of different vector registers. So we've got the difficulty of describing variables that kind of span pieces of registers. So our challenges were really that more often than the time we end up with variables being spread across bits of different kinds of storage, and we've got these pieces of registers, we've got these different address spaces, and then we got this SIMT execution model where we want to kind of select which piece of a register we want through a runtime expression rather than just being a static part. And then the other thing that kind of happened is we got a lot more complex expressions, and there's a great deal of benefit in being able to factorize the creation of the location descriptions, which isn't kind of possible currently, and which ends up in duplication of the expressions. So the things we kind of ran into with DWARF 5 that kind of made this difficult was we couldn't really describe variables that are on parts of registers. Neither statically can you talk about a part of a register or the runtime index. And that some features really only work when the memory is the thing, when variables are located particularly in memory, such as there are type attributes which describe the object that they're going to work with, but you can only describe that object using its memory address, which isn't helpful when it wants to sit in a register or some permutation of registers and memory. And then we have the problem that, if we wanted to use dwarf procedures to do factorization, they only accept memory addresses. We can't describe the vector register types because they're much wider than the base types that dwarf provided, other than just thinking of the pile of bytes. We couldn't create memory locations for particular address spaces, and then CFI had problems with it only accepted certain kinds of locations, didn't accept composites, couldn't accept address spaces, and then we couldn't deal with bit fields. So we wanted to kind of try and tackle all of these problems kind of in a reasonable manner. So we explored a bunch of different approaches, and the one we ended up kind of landing on seemed to be the simplest and provided us with the most benefits. It's really based on generalizing the execution model and providing a bunch of composable and constructible operations on that slightly different address space. And what we ended up with was a small number of operations we had to add that composed generally. And the alternatives we looked at ended up with a lot of specialized operations with special rules and context-specific semantics that were just much harder to deal with and for compilers and debuggers to work with them. And I think the major aspect is really that we're going to allow locations to be on the stack. And we'll talk about, well, what do we kind of mean by that? So our main goals really were we wanted to have an upstreamable GDB and LLVM compiler and GCC compiler support. We wanted to have it so that we could support other tools such as the Total View Debugger. We wanted to be definitely compatible, backwards compatible with DWARF 5. Obviously, we wanted to have the things that GPUs needed, but we didn't want it only to benefit GPUs. We believe that the changes we're kind of suggesting here will benefit other things beyond GPUs. So just a quick, what is DWARF? Well, it's really a standard way of specifying debug information. It's really describing how a source language entities, compilation units and functions and types and variables, how they map onto the physical hardware that the compiler decided to generate code for. And you embed it in the code objects, or you can split it off into separate files. you can answer questions like, this program counter, what's the source line? Or for this source line, what's the program counter? Or, where do functions start? Or where are source variables located? Are they in registers? Are they in memory? Are they in a combination of both? And it allows you to kind of virtually unwind the call stack so you can kind of get a view of how your program was running. And the big thing, one of the parts of it is that it really has it wants to describe a big diversity of how locations of entities, where they are. And those locations could involve runtime calculation, like the current value of the stack pointer. And there really is this big diversity of where location can be, registers and memory. Maybe they got optimized away and we know what the value is, or maybe they got optimized away and we don't even know what the value is, or they're spread across a lot of those places. So consequently, DWARF really has this rich expression language where expressions are basically evaluated on a simple stack, one operation at a time, in a particular context. The context kind of says whether you're trying to get a value or the place something resides. And, that context also tells, what program count you're at, or, so for some things, we actually need to know what an initial value to evaluate the expression within. And some of that context really comes from where the DWARF expression is residing. A particular attribute is for the purpose of computing a value, or is it for the purpose of computing a location of something, or maybe there's an initial stack value. So to try and go through a bunch of simple examples here, this is how DWARF 5 currently works. So the simple example here is we've got a source program that wants to have a dynamically sized array, and the size of that array is 42. But the compiler has optimized this. For example, maybe the value was, at a certain point relative to the stack pointer, or STPR, and we want to dereference that stack pointer to get to a memory location and read the contents of that. So this is the DWARF expression that kind of is going to achieve that. In this case, we're trying to evaluate this expression as a value. So that's kind of part of our context here. We're going to evaluate it on the stack. Here are the instructions we're going to evaluate, one operation at a time. So the first operation here is going to read the contents of a value. So we're going to push on the stack here the value. Notice that every entry on the stack, we've got a value and its type. The type has to be a base type as defined by DWARF, which basically tells you what the size of the type is, what its encoding is, is it a numeric or a floating point, and it's byte ordering, for example. So in this case, I've now got the value of the stack pointer. So the next thing I can do is I can dereference that, does the obvious thing, reads its context. Now I've got the 42. The result is a value, so the top value of the stack is the result of the expression. So if we look now at, say I want to say the location of a variable. So suppose I've got this variable here, and on a machine, the compiler decided to put it in this scalar register here. So in this case, my context, I'm evaluating in terms of a location. I'm going to use the word location. The DWARF spec talks about these as location descriptions. That's a little bit of a mouthful. So here, my first operation evaluates to get the location of a register. It gives the name of or the number of the register. The interesting thing here is DWARF doesn't evaluate locations on the stack. It has this separate conceptual location area here. So what we end up with is saying we're in a register here. And since we're evaluating context for location, then the answer is what's in the location area. So let's get a little bit more complicated. Suppose here we've got a variable, and it turns out that that variable was allocated in the scalar register, but for some reason, in this particular program counter, the compiler spilled it into memory, which is accessible, at an address plus an offset. This might be, the address of a stack pointer. So we're going to start off reading the value of the register again. So we've got that on the stack now. So next thing we're going to do is we're going to add our offset to that to get to the location that we want. Then we're at the end of the expression. We're evaluating it as a location. So DWARF conceptually implicitly takes that stack value and turns it into a location description, taking the value as if it were an address. And then that's our final answer. Sounds like Jeopardy. So let's get a little complicated here. So here I've got an example where I want a location. The variable is made up of a piece that's in a scalar register. It turned out that a piece of it was the compiler optimized away and was undefined. And then a piece of that register is actually in memory at a particular offset from a stack pointer. So I've got to take my stack pointer, I've got to indirect through it, I've got to offset it, and that's a piece. And I want to kind of describe this. And what DWARF has is the notion of a composite location made up of one or more parts. And each part is going to say how many bytes big it is, coming from whatever place we say. So first step, we're going to take the scalar register. So we got that in our location area. The next thing we're going to do is we're going to create a composite. So there's this piece operator. The first time you use it, it actually creates a composite. As we're going to see in a minute, as you use it subsequently, it's going to add parts on. And it's going to take its first part if the location stack has a location on it, the register. So now we're still in the process of making the composite, so it's incomplete. Our first part is going to be the register. And the for says, well, how many bytes of that register are we going to include? Next thing we're going to do is we're going to add another part. In this case, I have nothing on the location or the stack. So what DWARF says is that's equivalent to adding an undefined part. And again, we're going to say how many bytes it is. So we've now got two parts of undefinedness. Then the last thing we're going to do here to complete our variable is we have figured out that it's a memory address of, we're going to get our stack pointer here to read it. We're going to dereference that and add the 10, well, sorry, we're going to add the 10 to it, and breg is an operation that basically reads a register, adds a value to it, pushes a value on the stack. So then we need to now add that to our composite, and then again, DWARF says that, well, I want a location, I've got nothing in the location area, there's a value on the stack, and it's going to interpret that as using it as the memory address of that location. So now we've got our composite, we've got all the three parts of it. So then the last thing we do, we're at the end of the expression, so that now makes that composite complete. So what if we wanted to offset that composite location? We saw with a memory address, we can just use the add operator. Well, can we use the add operator with composites? So suppose I wanted to offset this by some amount, like 5 here, a little bit artificial here, but just suppose I wanted to do that. If I took that previous example and said, well, can I just do an add to it? Then the answer is no, because add only works on values, and locations aren't values, they're in this location area, so they're separate. So if the compiler wanted to do that, it would actually have to build a location which is just the part it wanted, and maybe we could build a composite using this expression to achieve that. But the observation here is that we don't have operations that kind of naturally work across these two divides. We've got the stack and we've got the location. So this really kind of led us to think about, well, what actually is a location? And a good way of thinking about it is that a location is really referring to some location storage. And you can think of location storage as just a contiguous linear organization of some set number of bytes. And you can think about all locations being this way. Global memory is a linear organization of this number of bytes, which is the size of the address space. A register, each one of the registers is a linear stream of bytes, which is the bytes that make up that architecture's register. Even composites, you can think of just being a location, a storage location, which is the bytes made up of all its parts. We didn't kind of show an example, but DWARF also has the ability to talk about memory, a value located in a where we don't know where it is, but we know what its value is, and it's an implicit location. So you can think of that as a stream of bytes. And then the undefined location is really just an infinite size location, which has every byte being undefined. So what this leads you to think about is that a location is really composed of what kind of location it is, a reference to its location storage, and then a zero-based offset. So if we think about that, a location could be put onto, if we could put a location on the stack and add new operations to work with that, then, for example, we could have an offset operation which updates the offset to a location to where you want. So now we can also modify existing operations to say, like, for example, deref operates by popping a location off stack rather than an address value and reads it. And so this means it will work with any kind of location, not just memory. And we can define some implicit conversions to make this all backwards compatible. So the key part of the extension is really making locations appear on the stack. And all DWARF 5 expressions then evaluate unchanged and give the same results. and this then allows us to get greater expressiveness. So if we take that view and start looking at some of those examples we had, we notice we've got no location area now, we just got the stack. So this example, we've got a variable which maybe it was existing in an SGPR, but maybe the compiler spilled it to a particular slot in a vector register. So this is something we can't do with current dwarf because we can't talk about a piece of a register. So what we're going to do is we're going to start off, we're going to get our register, and then what we can do is use our offset operator, and it's just going to update the offset of the register on the stack. And we can now, oops, sorry, one too many. And then this actually is now our location here. So this we can't do with current dwarf because you can only talk about the beginning of a register. And we could maybe solve this by making all of our big vector registers have lots of names, but this becomes rather intractable. There are so many registers on a GPU that this would quickly become intractable. And even if we did that, we still couldn't do any runtime indexing. I mean, this is a static index. Our next example will show a runtime index. So doing this gives us that composability. So this example, we've got the SIMT example where we had a SIMT value which is spread across two different registers of their particular lane. So we're going to take our register, we're going to put it on the stack. We got this lane operator. We're evaluating a context where we know we're at lane number 0. It depends, or lane number 5 here, depending on which lane our debugger was focused on. So this then gets us our 5 on the stack. Our slots are 4 bytes big, so we've got to multiply them by the 4, and that then gets us to our byte offset of 20. Now we can apply our offset operator, just like we did before. This can be the first piece of our operator. We kind of have the same rules of the piece. We start off first use makes a composite, and then we subsequent ones make offsets. We have a few conversion rules, which is the same thing that current dwarf does to get the backwards compatibility. And now we can move on to our second part, is a second register. We can get our lane offset, multiply it, get the offset, add it to it. And then finally, that is now our complete thing. So now we've got a composite that describes the two parts of the register there. And then we've got our composite being complete. So we made it a little bit more complicated. So suppose we took a previous example, and suppose the compiler spilled part of that register, the two registers to memory, and another part, maybe it knew what the constant value was. So here what we're doing is we can have our memory address. So here we've now letting ADRA return a location. We can add that piece to our register. We can now take a concept for that. Again, we can create an implicit location for that. So again, implicit's now our locations rather than in our location area. We can add that piece. And then finally, we did add an operation to explicitly end a composite. And the advantage of this is we can then build composites midway through as well. We're going to have multiple composites being built on the stack. Didn't really need to do that in DWARF 5 because you can only build them as the last thing. So this now has got a composite describing that example here. So address spaces were the other thing we needed to deal with. Now we've got locations as this thing that can be on the stack. What we can simply do here is, although DWARF 5 does have an XDREF, it doesn't really give you a way to actually build an actual address location that is in a locus area, and you can't compose it into composites. So what we're going to do is we get here we've got an example, we've got a variable that's in a particular address space. On a GPU, it's common that the stack pointer points not to our regular global memory address space, but a per lane address space that there are special hardware instructions for dealing with. It has swizzled memory so that each lane sees one linear view. So what we're going to do is our stack pointer points to this separate address space. Again, we've got an offset to get to our variable. So we take our register that we want. We can read its value. There's our stack pointer value. We can talk about our address space. In this case, address spaces, are architecture specific. Our one here is our per lane address space. We can then use this new operator to form an address space. So this builds us a location that takes the address value and the address space and builds us a memory location. So now memory locations just have this extra property that is their address space. And so that then becomes the result of our expression. So, and we can compose this so that anything that takes a location can now suddenly deal with locations that have address spaces. Bit offsets, similarly, we can just extend the idea that since locations have offsets, we can think about the offset as just not necessarily just being a byte offset, but being a bit offset. So in this example, we could take a register, we can then get our bit offset, and this could perhaps be a runtime calculation. And then the new operator here, we've got bit offset as opposed to the regular offset, and this now gives us the bit offset. So now we've got our little slice of the register. Again, something that current dwarf, although there is bit piece, it really only works with composites. You can't kind of do it in other locations. Other benefits we have, once we have locations generalized on the stack, there are other places where dwarf says the expression is evaluated starting from a value that's on the stack, or it has this push object address, which uses a context, which is the object address. And currently, we can only think about those as memory addresses. Since locations can now be on the stack, we can now think about these things with things in registers or in composites, which is really helpful for GPUs because the compiler tends to put things in memory and registers and composites them a lot. It also means that the call which dwarf has to call dwarf procedures, we can now use that because we can have locations of any kind to be on the stack, and we can pass them in and out through the call. And again, that benefits us to get this incremental increase, building up of the dwarf expression. So CFI, similarly, now we've got locations as generalized on the stack, and we needed for the GPU to talk about CFI where things were in address spaces or in composites. We've seen how registers could be spilled into multiple pieces of registers because of the SIMT work. So that generalization allows us to deal with that. And then the other thing we kind of added is on GPUs, for example, as we call a procedure, it might be that we only spill registers, that are callly saved, if the exec mask, which controls which lanes are active, are currently showing that that lane is active. So we want to actually conditionally, when we're unwinding the stack, virtually unwinding the stack, say, well, if a bit in this register is a 1, then get it from here, and if not, get it from somewhere different. And then that meant we also needed a way to get the value of the exec mark as it came into the procedure so that we can actually use that as part of the expression. So we added operations to deal with that. The bit select here is really just something that composes with building a composite out of location descriptions. And then the final thing we kind of did was for multiple places, DWARF 5 introduced has the concept of location lists, and you can use these for implicit pointers and calls. They can refer to a debug information entry that has a location list. So we extended the idea of a location to not just be that it only had one thing. We allow it to have a list of single locations. So for any particular location we have on the stack, it might mention that it's in more than one place, which really mirrors what location lists are. And then we extended the operations so that, for example, the offset operation does an offset on each one of those multiple places it can exist. And DWARF 5 kind of defines operation expression location lists separately, which is fine for DWARF 5 because it only allows you to build that location list as the last step of the expression. And by generalizing, we really now can allow location descriptions to kind of be built midway through. So this kind of naturally fell out that we could now unify those. This is just a summary of the new operation we added. I think we talked about most of these. In CFI, we added a couple of things for address spaces, and then we have some attributes we kind of added to support vector base types. And then we built on that to do our divergent lane control. Didn't really talk too much about that, to have attributes to support that. Our current progress is that in GDB, we've kind of got an initial implementation that Zoran's done in that, and Pedro's been working on that. We're also currently working on LVM compiler support, and TotalView is doing implementing this to see how it works out. Mentor Graphics is working on the GCC part. I think Andrew Stubbs is going to do a demonstration of that on Thursday, I think. You can see the full description of what these extensions are, and then this link is to this is kind of the normative description of it, and then this gives us our AMD GPU architecture for it. Really would like to thank a whole bunch of people that helped us get so far. Thanks to GDB maintainers. We've been working with ARM and HPE. We're talking with Marcus at Intel they're working on GPU debugging as well. And also working with Lawrence Livermore Labs and Oak Ridge Labs and Mentor Graphics, as I mentioned. And a big shout out for John Del Signor, who we spent a lot of time working with to try and figure out where we wanted to go. So in summary, the DWARF expressions, we've generalized them to our locations on the stack. We've got some new operations that are composable, consistent, backwards and compatible. We've got the support we need for GPUs, but we also believe that they support other things beyond GPUs, such as CPUs. And that gets us to the end.
Thank you very much. That was fascinating. Anyone has any questions? Richard.
Yes. So if the register file were available in global memory, what's the issue with the DWARF expressions not being powerful enough be solved if you express all these as addresses of that memory region?
Well, if it's in, yeah, I mean, you could then just use the memory address and everything would be copacetic, yeah.
So like if you introduce a magic global GDB rex symbol that the consumer then just maps to the registers, that you could express at least the location expressions via such trick?
Yes, you'd have to come up with a way that you would want to have some magic memory. Presumably you'd have to carve out these addresses can't be used for regular memory. So I guess you'd have to maybe have a bigger address space than you would normally, because your normal address space might span the entire, address space. So yes.